So now let's consider a little bit more practical aspect of neural network development, and in particular we will be looking at one of the leading platforms of frameworks for a design of neural network architectures. There are plenty of such networks. One important aspect I would like you to take into account looking at this picture is despite the variety of platforms, you can arrange them according to the depth or closeness to the hardware. So on the lower level, you have different kind of computational devices like GPUs or TPUs, etc. And then you have some abstraction layer in terms of drivers. If you're talking about NVIDIA devices, it goes to CUDA, and then a higher level CUDA deep neural network package that allows interfacing a higher level computational packages like mentioned here at this layer with those hardware processors. And we can stick with Chainer, PyTorch, Tiana, which maybe is a little bit outdated, TensorFlow, CNTK, etc. But also we have to take into account that there is a higher level of abstraction that allows coding with a little bit less effort by combining neural networks with building blocks that maybe by combining neural networks of building blocks of predefined structure, and higher level provides you a higher complexity building blocks that can be combined into a neural network structure. So many people may have own opinions, and usually the selection of platform is done from some business requirements or from some past experiences. So we are not going to compare all those platforms because it will take a lot of efforts and time. Instead, I would try to argue that PyTorch would be one of the best candidates here. And here is the list of reasons why I think so. So first important aspect that it is an automatic differentiation engine that allows computation of all the backpropagation rules that were mentioned before. However, it is not something that differentiates it from all other engines mentioned earlier. So I would have to mention that it has nice and transparent development debugging support, so you can print contents of every tensor every time. And there is a rich ecosystem with different packages and pre-trained networks and integrations. And it has been around for quite a while, so it is production ready. It supports distributed training and various deployment options to common cloud providers, and it has already been serving for many companies that rely on neural networks quite heavily. So let's take a look closer what neural network is in terms of PyTorch. So first of all, we have to switch from a common neural network representation that we have here or some mathematical representation that we have here to a graph of computations. So if we want to compute a variable y that is mentioned at the math formula below, we have first refer to the function ReLU that takes two arguments, b2 and w2 that is multiplied by ReLU, and which in turn takes into account two other arguments and so on and so forth. This we call a computational graph because every node is aware what result does it produce, and also it knows what arguments does it take. So we can go through this graph either in the forward direction from the initial arguments to the target, or we can go in the opposite direction from target to the arguments. And it is important because, as we saw, computation or optimization of the neural networks essentially goes in both directions. So, as for building blocks that are present in PyTorch library, we can mention tensors, which is data representatives, essentially matrices of certain size. We'll take a look into seminar and more details, how you can initialize and how you can do some basic transformation with the tensors. Another component is a graph I mentioned before, and here is the mathematical representation of a graph, and on the right there is a symbolic representation of this graph. Variables that we can change, I mentioned variables that we can change, weights, mentioned here in pink color, and other variables A, B, C, D are something that we know a priori. And all the operations are performed using special math functions from PyTorch. They are highlighted or provided in the documentation page in more details. So, due to the fact that all formulas, including loss function, that depends on variables of the training dataset and variables that we want to tune, weights of the neural network, can be expressed in this computational graph form. We can rely on the automatic differentiation that is happening every time when we call a certain function. So when we make a call, this computational graph is built, and we can go and compute it from the initial parameters or variables to the final result. And if we can build such a graph, we can transverse it or reverse it and go in the opposite direction. So if we know that L is computed as a difference between a constant and D, we for some reason want to estimate the sensitivity of L with respect to D, we know what nodes of this graph we want to go to make this quantitative assessment. And for example, if we want to compute a derivative the W4, we have to compute a derivative dl by dd, and then dd by dw4. And all those expressions of derivatives can be related to the computational graph elements. So here is the way how you can compute the forward pass in such a graph and the backward pass when you send the gradient estimations back from the parent node, or sorry, from the child nodes to the parents. So to retain this information about the gradients, every tensor has two special attributes: grad fn, which refers to the mathematical operator that has created such a variable, and attribute grad, which contains the gradient value per tensor element. So if we define a graph using this piece of code, tensor, 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 two more tensor, the final tensor, and the ultimate loss function that depends on all elements before. And we can print and examine what is the function that has created each of these tensors. So if we print those two gradients, we get such answer like here. Since a is independent variable, its grad fn equals to none. And when we compute a function, as I mentioned before, those functions are inherited from the class torch autograd function, and there is a method that is called forward. So it computes a node output and buffers it, and method backward that stores incoming gradients and passes it further up the graph. So when you receive a gradient from a parent of D, dl, d, you can add own local gradient and pass it back to other functions that has created this tensor D. And this is what is written in this piece of code. You can spend your time looking at this by just pressing pause in this lecture. So, and since the passage of the backward stores the grad values in element of the tensor, so it is a special attribute, and then we can make a gradient descent really simple by just updating new weights with a difference between previous value and the step that goes in the direction opposite to the gradient. So, and all the functions that we built, all the network architectures are represented as such a graph of functions that is called dynamic graph. And it is important to remember that the buffers that store information about the gradient may require to add information when you have non-trivial connection between network nodes. So for example, if you have a parent node that depends on two children, or sorry, that passes the information to two children, and the gradients from those children coming back to the parent should be summed up, and this is happening in under the hood. The only thing is that training of a neural network might be complicated, and it is difficult to say when one epoch of the training ends and when the next is starting. And that's why sometimes, well, at the end of iteration, you have to clean the gradient accumulated during the previous step. And it is performed either by calling the method 0_ for every model tensor, or by using Optimizes zero_grad method, which is a little more elegant and thus more preferable. So when the network is trained, you don't need to compute the gradients, and thus you can save a little bit of resources, computational resources, if you do not allow to forbid creation of these gradient elements in the computational graph. And this is controlled by the attribute requires grad. So effectively it can save a lot of memory if you just want to load the network for the inference. So here is the example how you can load a network, and if you want to quickly compute or retrain just the final layer, it is possible to do so by effectively disabling computation of the gradients for all the elements in this network besides the final layer, which is added, and when we pass this object to optimizer, it is the only tensor that is being trained during optimization procedure. The elegant or the syntactic sugar to temporary disable computation of the gradients happens with the command mentioned on this slide. So PyTorch supports all mainstream computational hardware like GPU and TPU. There is a plenty of building block element even on the layer of PyTorch, and all those are first-class citizen in torch.nn module, and all those are inherited by inherit class module that provides two basic elements that you have to redefine, which is init, that defines the architecture of the network, and forward, which does the computation involving building blocks created at the constructor. There is a bunch of loss functions that you can just pick from the shelf, bunch of activation functions. And optimizers, we mentioned SGD, Adam, Hermes Prop, but you see that there are plenty of others implemented as well. And surprisingly, there are parts that are not related to training of the neural network, but also important task of data loading. So I encourage you to look at data sets, tensor data set, and data loaders and data samplers that effectively deal with various kind of data, CSV, directories of images, and can download it from network and whatever. Supports a great variety of different formats, as well as getting data that is part of PyTorch distribution in Torch Vision library, for example. So the ecosystem is quite extensive. So there are high-level primitives, way how to work with graphical network, training distributed network, scikit interface with fit predict methods, optimization, and many other things, which I would encourage to look. Other interesting points for your own examination. And just right time to finish this part by concluding that we've looked at the PyTorch as solid, flexible, production-ready foundation for real-life deep learning applications. And the main component is the auto-differentiation engine, which is called Autograd, consisting of such building blocks as tensor and functions. It supports all the main computational devices and has quite a rich ecosystem which you can refer to in case you need either support or some pre-built components. Most likely, if you need it, you're going to find it there. Thank you very much for your time and attention, and see you during the next lecture.